Okay, put on your detective hats, guys, because today we're investigating a bit of a crime scene. The victims, literally thousands of Cambridge IGCSE Physics students. And the crime, hemorrhaging marks on questions they actually knew the answers to. Welcome to This Explainer. Today, we're acting as data detectives. We're going to rip apart the Cambridge Physics 0625 syllabus to decode exactly how marks are won, and honestly, more importantly, how they are brutally lost in the high-stakes topic of pressure and liquid pressure.
I want you to imagine sitting in your exam hall. Your heart's pounding, the clock is ticking down. You spend 3 minutes perfectly crunching the numbers on your calculator, and you write down the final answer. It's mathematically flawless, and yet, the examiner awards you 0 marks. Absolutely 0. No way, right? Well, this isn't just some nightmare scenario, this is a reality pulled straight from past papers. To understand why this happens, we have to strip everything back to the basics.
Which brings us to Section 1, Core Principles of Pressure.
Okay, let's dive into this. Before we can start gaming the Cambridge mark scheme, we really need to load up our foundational weapons. You just cannot survive these exam questions without a rock-solid grasp of what pressure actually is. So, pressure, or lowercase p, equals force divided by area. It's simply the measure of force applied per unit area. But listen, examiners don't just want you to recite this equation like a robot. They want you to understand the variation. If you increase the force on the exact same area, pressure goes up. But if you keep the force the same and spread it over a massively larger area, well, think of it like wearing snowshoes instead of stiletto heels in the snow. One lets you walk gracefully, right? While the other gets you stuck and completely ruins your shoes. Because the area is bigger, the pressure goes down. This inverse relationship is your absolute ground floor.
Now, this builds into the territory where students usually start to panic, which is liquid pressure. The formula here is delta P equals rho, which is the density of the fluid, times g, the acceleration due to gravity, times delta H, which represents the change in depth. Basically, it dictates the pressure beneath a liquid surface, telling us that pressure changes based on 2 totally key variables, depth and density. The deeper you go, or the denser the fluid, the higher the pressure. Consider the Mariana Trench. The pressure down there is over 1,000 times greater than at the surface, and that's entirely because of that immense depth combined with saltwater density. It looks kind of intimidating on paper, but honestly, it's just a recipe of variables.
But here's where the trap is set. Listen to this direct quote straight from the Cambridge syllabus. Top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. What that actually means is the assessment framework prioritizes analytical depth over superficial breadth. In plain English, rote memorization is totally dead. If you just memorize those 2 formulas without understanding how they interact in a weird, unfamiliar scenario, like, say, a submarine in a freshwater lake versus a saltwater ocean, the examiners will literally see right through it.
Which actually brings us to a massive question. In just a moment, I'm going to reveal the single hidden examiner clue that changes a pressure answer completely. It's the secret difference between a B grade and an A star. But if I explain it right now, it won't quite make sense. First, you really need the methodological framework that makes this clue incredibly obvious.
So let's look at Section 2, the Method Mark Lifeline. This procedural framework right here is your psychological safety net for the exam. When you face a really complex liquid pressure question and your mind just goes blank, you don't panic. You rely on this exact step-by-step, deconstruct, solve, and evaluate sequence derived straight from the source. Step 1. Identify the key elements given in the text and tables. Step 2. Apply the relevant principles. Ask yourself, is this a standard force area situation or a liquid pressure situation? Step 3. Execute the analysis with crystal clear working. Step 4. Verify your results. Do they actually make logical sense? And finally, Step 5. Present it all in the appropriate format. Guys, this isn't just good advice. This is literally how the mark scheme is structured.
So the absolutely crucial point here is show your working. This is a massive examiner alert. Remember that student who got the 0 mark tragedy from the beginning of our explainer? Yeah, they completely failed to show their working. The Cambridge evaluation process specifically awards method marks. Even if you completely mess up the final calculator execution, showing this systematic 5-step process is exactly how you scrape back 2 or 3 marks out of a 4-mark question. Your process is your absolute insurance policy.
Moving right along to Section 3, the examiner's playbook, Top 3 Mistakes.
Let's pull back the curtain even further, shall we? We've pulled direct, exclusive insights from the principal examiner reports, and here are the top 3 critical missteps that just drain points from otherwise really smart students. Number 1, forgetting to include the proper format. That means missing your units, like pascals or newtons per square meter. Number 2, failing to check that format and presentation. Sloppy annotations will for sure cost you dearly. And number 3, this is the ultimate killer. Answers are not specific to the context given. Students write these generic textbook answers instead of actually applying the physics to the specific submarine, or hydraulic press, or weather balloon mentioned in the prompt.
To stop you from making these super frustrating formatting errors, here's a quick memory hack directly inspired by the source material. Create a mnemonic using the first letters of key pressure terms to basically lock in your presentation checklist. For example, use the variables P, F, A, rho, G, H to remind yourself, please format answers really good here. Okay, I know, it sounds incredibly silly, but trust me, in the heat of the exam, having a quick mental trigger to double-check your format and units is a literal lifesaver.
But formatting is really only half the battle. Listen to this quote from a senior examiner. Why do students find evaluating evidence and drawing conclusions so hard? You know, it's a really great question. It's because identifying limitations, questioning assumptions, and actually evaluating the quality of the evidence requires a totally different cognitive muscle than just plugging numbers into a calculator.
Let's put that to the test in Section 4, Spot the Error, Flawed versus Perfect Answers. All right, it's time to play Spot the Error. We're going to apply our framework to a classic Cambridge-style comparison. Take a look at the flawed approach. It's just a naked final number without any context, working, or units. That is the exact trap we talked about at the start. Now compare that to the top band perfect approach. We have clear data extraction from the question. The formula delta P equals rho G delta H is explicitly stated. The steps are clearly shown. And this perfectly resolves our open loop from earlier. That hidden examiner clue? It's the specific terminology tied to the context. The perfect answer doesn't just generically state depth changes, it says the depth of the salt water beneath the hole changes, utilizing the exact context clues provided in the prompt to secure those elusive application marks.
Which leads us perfectly into Section 5, the unresolved mystery, linked to practical skills.
But wait, even if you completely master the formula, the working, and the context, there is still an unresolved mystery that can completely derail your score. Because in Cambridge Physics, theoretical calculation knowledge is practically useless without the linked data analysis skill. Top-scoring candidates must demonstrate evaluative thinking and practical investigations. You have to be able to identify limitations in an experiment. You must question the assumptions made by the setup. You need to consider alternative interpretations of the results. And absolutely critically, you must be able to extract precise data from highly complex tables to actually justify those conclusions.
Which leaves us with a pretty massive cliffhanger. You know exactly what you need to do, right? You need to evaluate evidence and analyze complex tables. But how exactly do you extract this data to draw evidence-based conclusions without losing those really tricky practical marks? What is the specific technique to rip the right numbers out of a deeply confusing experimental table? Because without this skill, your perfectly formatted theoretical knowledge basically remains incomplete. Well, the answer to that vital data analysis mystery is exactly what we uncover in our next explainer. You do not want to miss the missing piece of this puzzle. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Keep questioning, keep analyzing, and I'll see you in the next one to solve the final piece of the pressure puzzle.